Welcome to the session Topo Reconstruction Skeleton Process of the First Steps course. Here you will learn how to reconstruct a topology optimization result into a solid rod framework. You will voxelize a topology optimization result, reduce it to its skeleton and clean the curve network. Then you will create solid rods based on the curve network. Adopting this feature for your projects can be very helpful when working with rod-shaped topology optimization results, for example brackets. For the skeleton reconstruction process, we need two inputs. One is the result of the non-dimensioning discrete topology optimization, and the other one is the non-design space, which you can see here. And here we have the isomesh of that optimization. We have to go through 4 different steps in order to obtain our rod-shaped solid body. And one thing that I will mention right in the beginning, this is a bit of a simplification. So normally you would have to do a cross-section optimization of those pipes or rods, which we will not do in this lesson because it kind of exceeds the borders of an easy first steps course. So we will only define rods or pipes with a consistent cross-section. So we will start with creating a voxel space from the isomesh that we obtained from the topology optimization. We will then extract a clean curve network from it, create a solid beam network out of the curve network, and then unify it with the non-design space and fillet the edges. There's a difference when reconstructing a topology optimization result with the skeleton and the quad remeasure process. So if you use the quad remeasure process for like volume bodies, the process can be automized completely. It works for all the results. With the skeleton process, however, you have to manually adjust the settings. There are very many settings, especially in the clean curve network, that you have to take care of. And if you just leave the settings as they are right now, or not right now, but in the end of this tutorial, and you plug in your own input, probably the workflow will fail because you have other dimensions. This is a very, very small cantilever beam, and probably your parts are much larger. So yeah, it definitely is worth going into this details and taking a look at the inputs. So let's voxelize our isomesh result. Use the create voxel space component and plug in the isomesh, and then we will use a resolution of 0.6. This also highly influences your curves that you will later extract from the skeleton. So also here, play around with that resolution. Generally, it's a good idea to have like 2 or 3 voxels at least representing one of those rods. Okay, now we will make this symmetric. If it already is, it doesn't hurt to still use this component just to make sure. Plug in the voxel space, and then we will use the ZX panel. And we will get a warning here, but we can ignore it and now have a symmetric result. And we can continue to our next step to extract a clean curve network. First, we will skeletonize the voxel space using the skeletonized voxel space component. And what this component does is removing the outer voxels until a voxel space with a thickness of 1 voxel is reached. And then polylines going through the middle of the leftover voxels are created. And we will use this non-design space as a connection because we would like the voxels or the lines being connected to the non-design spaces, and plug in a connection tolerance. And let's check out the result. You already see the voxels that build up the skeleton, but let's also take a look at the curves. These are our curves, and actually I prepared down here some basic containers so that we can later compare the different states of the curve networks. We will now clean up this curve network, because right now, as you can see, we have like some short curves and they're very wonky, and yeah, we can't further process them into pipes or rods. So we plug in the curve input and then again the connection geometry, which is the non-design space or the non-design spaces, and then also a connection tolerance. And let's blend these out and the curve network in. It still doesn't look really nice. So let's remove some short curves and change the rebuilding degree, the simplification, all these settings. So we will remove short curves until we can't see those individual curves flying around. That looks good. And set the curve rebuild degree to 1 to get straight lines and simplify them entirely. Okay, so I will blend in the non-design space so we can actually have a look. This looks good to me. They are not connected yet. And this is why we need the next component, which extends the curves to the non-design spaces. So plug in the curves and the non-design spaces, also the overlap length and the surge tolerance. And as you can see, now we have a curve network connected to the non-design spaces and actually overlapping with the non-design spaces, which is important when we later create those solid beams and we want to unify them with the non-design spaces. So again, I will connect these curve outputs so that we can actually compare them now. So we have these skeleton curves. This is our first attempt. Then we simplify them and clean the curve network, and then we extend them to the non-design space. And as I mentioned before, the result is very, very sensitive to these settings, so it's worth taking some time and testing which settings give you the best result. And now we can actually continue with the third step, which is creating a solid beam network. We will construct pipe curves from the clean curve network that we have. Plug in those curves and then use this radii. And as you can see now, we defined the curves and all those radii. Right now we just have one radii or one cross-section radius for all the curves. This is what would be optimized in a cross-section optimization. But right now we will just work with one radii over the whole curve network as a simplification, and use this list of pipe curves that we have to create a pipe network mesh. Give this a number of sides to make it a bit smoother. Blend in the edges. And here you can see the result. I think it looks quite nice. You can up the number of sides to get a smoother result. Also change the segment length here. Okay, now we can actually transform this pipe network mesh into a solid body, so we don't have a mesh anymore, using the mesh to solid component. And we get this solid body. As you can see, towards the end, those beams are slimming down a little bit. That's why it's important to have this overlap between the non-design space and the beams or the curves back at that state, so that we won't have this effect later in our final design. I just plugged this into our output and it will be unified with the non-design spaces, resulting in this design. As you can see, we have some overlapping going on. All right. So now we have unified our result and we just want to fillet the edges. Get the fillet edges component on the canvas and plug in the unified body. And now we have to tell the component which edges to fillet. And I will just use the basic curve container to show them. These are the edges that have been newly created by unifying the non-design space with this beam network. And these are the edges that we choose to fillet. Here I have the input for an edge tolerance and the radii. Now the fillet edges component will run. I would like the first fillet type, and as you can see, the component fails to calculate and we get an error. And what we can do in this situation is use the auto decrease radius. So the entered radii will be multiplied with the decrease factor to reduce it. And right now this is only tried one time, so I will just up the number of attempts and see if this helps. The decrease factor is quite high, so we will just slightly reduce that radii. And now the component is recalculating and hopefully works now. So this is our body with fillet edges, which you can see here. And we can plug this into our output and now have our reconstructed topology optimization result, which is a solid body and a beam network. In this session, you learned how to reconstruct a topology optimization result into a solid rod framework on the example of the cantilever beam.